Hello, Microprofessor fans. Let's continue our exploration of the force system for the MPF-1 Plus Microprofessor and pick up where we adjourned last time. In my last video, I demonstrated basics of reverse Polish notation, RPN, and I also demonstrated the interpreter, for example, how you can use your microprofessor as an HP-style RPN calculator, right? Little reminder, so here we put 2 on the stack, then we put 3 on the stack. So, and remember that the stack is a last in, first out LIFO data structure, right? Now 3 is at the top of the stack, and then there is 2 underneath, below 3, right? And then we invoke to the topmost 2 elements of the stack. We invoke the plus word, the plus operation, right? That then basically consumes these 2 top stack entries, right? So 2 and 3 are gone and fed into plus, and plus leaves 5 for us instead, the result of the addition on the top of the stack. And then we can retrieve the the result from the top of the stack using dot, right? And dot is also printing the result, right? And after that, of course, the stack is empty, right? So if we try to get another result from the stack, right, then we will get an error message. So remember, there's .s, which prints the whole stack in the order in which it was populated from bottom to top, basically, right? Or from first to last, and last is the top element. Or you can use dot to pop an element from the stack and print it. And of course, here we are now getting an error message number 1, which means stack is empty, right? So, and we were interacting with the interpreter here, right? So the semantics of the interpreter is, what the interpreter basically does is, when it can parse a number, when it recognizes a number, such as 1, 2, 3, it basically puts that number on the stack, right? But if it encounters something that it can identify as a force word, right? And all the words are stored in a linked list, basically, which is called the dictionary, the system dictionary, that comprises the vocabulary of the system, right? So, and if it recognizes a word, then it puts in basically a pointer to the machine code implementing the runtime of that word, right? And when that is being executed, then when we hit enter, then of course the machine code routine behind that plus operation is being executed. And some of these words are defined in machine code, right, and are in the ROM, but many other words are actually defined in terms of force itself. And this is what I mentioned previously. So force is basically largely written in force itself, similar to languages such as Lisp. Lisp has a very small core of system primitives, right? Everything else is built in Lisp itself, basically, and this is the same in force. For example, the interpreter that we are interacting with now is written in force itself. And the same also holds true of the colon compiler, right? And and of course, I mean, interpreting and finding the machine code basically for a force word going through the dictionary requires time, right? So it requires a search through that linked list until the interpreter finds the right word whose machine code runtime semantics it has to execute, right? And you know, the dictionary is quite large actually, so you can get a list of all the words in the system in the dictionary using vlist, vocabulary list. And you see that this is not a toy system, right? So in these 8 kilobytes of ROM, you have like really a large vocabulary. I mean, hundreds of words, right? I haven't counted it, but I think it's like close to 200, 300 words, which are defined in that EEPROM. And all of this in 8 kilobytes of ROM, right? And that, of course, explains why force has been so popular and successful in the computers and early microcomputers of the 1970s and 1980s, because memory was a scarce resource, and the performance is really, you know, next to kin of machine language and assembly, right? So, yeah, and I demonstrated how to use the colon compiler and how to make your own user-defined words, right? Like add 3, and notice that add 3, we are getting an error message here because we haven't defined it yet, right? 0 means word is not defined, and we can invoke the colon compiler using colon and then give it a name, and then all that does it puts 3 on the stack and it invokes the addition word, and of course we need the other operands and also on the stack, and then we print the result and we terminate the definition with semicolon, right? And now the word is part of the dictionary and we can just use it as if it was a built-in word from the beginning. And yeah, so force embraces a philosophy of bottom-up programming, I would say, right? So first, let me demonstrate what I mean by this. First, I told you that usually I don't use or do hello words, but here it is in the interpreter, right? So there's also a print string basically word in force, right? And this is the dot quote. Actually it's a double quote, right? But I think it's only called dot quote. And this is how we print hello world on the arbitrary string on the screen, right? And notice that you actually need a leading space here. So if you write it without the space, right, hello, and you're getting an error message. And again, of course, the error message is that the word is not defined, so the space is actually part of the name of the word, right? Otherwise the interpreter doesn't find it, right? And so we could, you know, define our own hello world word and just, you know, print hello world on the screen. So rather than just typing it into the interpreter only in direct mode as I just did, we define our own hello world program, right? Which we can then of course now invoke with our user-defined hello world word like this. And there it is, right? And now let's forget about this. And I just said, okay, so force really embraces a philosophy of bottom-up programming. And in terms of hello world, that's a little bit of a silly example, of course, because it's so simplistic. But what it means is basically you start by defining more basic or more simple words, right? For example, we could have a word that only prints hello, right? And then we could have another word that only prints world, and then we would write a more complex or more, you know, compound program, hello world, that would use our previously defined words in a bottom-up way, right? First we invoke hello and then we invoke world, and of course the program does exactly the same now, but we have used, we have defined 3 words, 2 more basic ones and then 1 more complex one, hello world, which uses our basic words. I think that's clear, right? So, but what force does not allow you to do is to use forward references, right? So if I say, okay, hello Mike, I use my hello word and then I want to also use a word Mike, right? And of course now I'm getting the error message again because Mike hasn't been defined yet, right? So a more top-down style of programming, right? I put in something which I haven't defined yet, but which I'm going to define later, is not possible in force directly, right? Because it cannot deal with forward references, right? So if the word is not defined at compile time, you get an error message. There's no thing such as a 2-pass compiler that violates the philosophy of force, basically, right? So rather you're supposed to, you know, build your program in layers or strata, basically, right? And there ought to be no cycles and no forward references. There is a way around it, right? And of course, if you want to define something like a recursive definition, right, which is, for a Lisp programmer, this is bread and butter to come up with your recursive definition, but unfortunately, that's of course also not possible in force, right? So at least not directly. It is possible, and I'm going to demonstrate how we can achieve this in my next video using compiler extensions and something that's called vectored execution over variables. And well, that's kind of a little bit more advanced, right? And so I don't want to demonstrate this here. So it is possible, after all, to deal and write programs that have forward references and also recursive programs, right? But it requires a compiler extension, and we are going to look at this in the next video. So, but even a simple recursive loop is infinite loop here, right? High, and it prints high, and I, want to invoke in a recursive loop high itself again, right? It doesn't work because even for the word that you're currently defining, right, it is not defined and known in the system until semicolon terminates the definition, right? So again, we are getting the error message here that high, the recursive call of the word itself, is not defined at that point yet, right? So, and again, there are solutions to this, and I'm going to demonstrate this in my next video. But for now, we want to take a look at some other required vocabulary that we need in order to write our more complex force programs, right? And one thing, of course, then, okay, if you can't have recursion, right, so how do you implement your loops? And there's a cure for this, right, which is, of course, the do loop statement. So let's demonstrate this directly here in the interpreter. So first you put the upper limit of the loop on the stack, right, and then the lower limit. So say we wanted to have a loop which counts from 1 to 3. So I put upper limit plus 1 into the on the stack, and then the start value for the loop, right? And then I just use a do statement. And now within do, in the body of the loop, there is the I variable, which allows you to retrieve the current loop counter value and put it on the stack, and then we can print it, right? And then we terminate our loop body using loop, right? And this is how we would have a loop that counts from 1 to 3. But there's a catch, right? So loop is something that only works in the compiler mode, right? So you cannot execute loops directly in the interpreter, right? Because loop itself is actually something which is, unlike in C in the compiler, right, is something which is defined in terms of compiling force words, right? And it only works in the compiler because it actually needs to generate code, and it cannot do this in the interpreter, right? So let's write our test word here, and let's put the loop definition in here. So we want to count from 1 to 3. We put 4 on the stack as the upper bound of the loop plus 1, and the start index is 1, right? And then we have loop. Actually, it's do, right? And then I'm using I to retrieve the value, and then loop. Okay, that compiled, and now I can invoke it, and there you have it, right? And once again, if we try this directly in the interpreter, right, then it fails. And we might want to look up what it means, this error message, right? Number 17. So if we look at the at one of the appendices, then you see here we have a list of force error messages, and number 17 means the word cannot be used outside the definition, right? And this is exactly what happened. So you can only use it when you're writing a definition inside the compiler mode. All right. Excuse me. So remember, I mentioned that I always like to implement a version of Factorial, right? And I just explained to you that forward references and recursive definitions are an advanced topic which requires compiler extensions. So we are not going to do it now, but we are going to do it in the next video. For now, I want to give you the iterative definition of the Factorial function, right? And I just showed you how the loop works. So all we got to do is, let me just type it in. So and then I explain it later, right? But this is how that would go. Actually 1, yeah, 1 plus where is the multiplication? Yeah, so really only one line, that's all there is to it, to an iterative definition of the classic factorial function. And 1 times 2 times 3, or 3 factorial is of course 6. Into 4, it should be 24. And at some point, you know, around 12 or 13, it overflows, right? Yeah. So 11 is the largest factorial we can compute in that way. After that, it overflows because it's, you know, unsigned integer. Sorry, signed integer here. But I mean, I could push it a little bit further by using a signed integer, right? Yeah, an unsigned integer. Sorry. And remember, there are also doubles, so meaning 32-bit integers, right? So, and arithmetic operations for these, but it doesn't add to the discussion, so I'm not going to do it. So let's forget about our version of factorial, and let's enter it again and explain what's going on. So remember that a loop basically requires first the upper index, right, and then the start index of the variable, right? And within the loop, of course, we then kind of need to multiply things together. So we need an initial argument, right? So first, say we want to compute the factorial of 3, we put 3 on the stack, right? And now, obviously, what we want is a loop for 1, right? Just as I demonstrated it, upper index plus 1 and start index, right? So that we can multiply 1, 2, 3 together, right? And so this is obviously the number from the stack plus 1, right? 3 plus 1. Or let's just write it the way I do in the code, right? 1 plus. And then of course I need the do body here, right? And all I do is I multiply the current value of the loop variable with the other value that's on the stack, right? And we got to make sure that we always have the second operand there. And yeah, so that's basically the loop, right? So to make sure that this succeeds also for the first iteration, right, we got to make sure that we have also an additional 1 on the stack, right? So we invoke 3 factorial, right? So we have 3 on the stack, and then we got to make sure that we put another 1 on the stack, right? Because we got to multiply, and multiplication obviously requires 2 arguments on the stack, right? So we add the additional 1 on the stack, and now in order to get 4, now on the stack we have 3, 1, right? In order to add 1 to the 3, in order to get the 4, we have to swap those basically, right? So that results in the order on the stack is now 1, 3. 3 is on top, which is now of course perfect because now we can apply our 1 plus operator here, right? In order to get 4, right? Now at that point we have on the stack 1, 4, and we can put our start index for the loop on the stack, right? So 1, 4, 1. And now then we can actually execute the loop. And so this is exactly what's happening in this definition of factorial, right? So we already have the number of which we want to compute the factorial on the stack, right? Which is 3 in this example I just showed you. Then we put our 1 on the stack. Now in order to get hold of the 3, because we need to add 1 for the upper loop index, right? We got a swap. Now instead of 3, 1, we have 1, 3. We can then get our 4 by adding 1, right, to the 3. And now we put the lower, the start index of the loop on the stack as well. And now we can actually run our loop. retrieves the current value, which goes from 1 to 2 to 3, right? Multiply with the other value that we have on the stack, right? And remember, this is the 1 we initialized it with 1, so the first loop iteration says 1 times 1. So multiply consumes those two values from the stack. Right now 1 and 1 are gone from the stack, and it puts its result on the top of the stack, which is of course 1. And now again we have, for the next round in the loop, right, we have again the result of the previous iteration from the multiplication on top of the stack, and can multiply this with I, with the next index, right, again, right? And then we terminate our loop body and we just print the result. So yeah, it's as easy as that. And apparently, sorry. There you go. All right. So there's also ifs and else, and we are going to need ifs and else if we want to write a recursive definition of factorial in our next video. For now, I just want to show you how that looks like, right? And let's forget about excuse me, the factorial function, and demonstrate how ifs and else and relational operators work and force. So basically, you put again the operands on the stack, right? And then you use one of the relational operators, for example, smaller than, right? Is 2 smaller than 3? And that again consumes the two values. And what's the result? So the result is now basically a Boolean, right? And force uses 0 and 1 for the outcomes of the results of these relational operators. So we would expect a 1 now, right? Because 2 is smaller than 3. But the other way around, right? You would now expect a 0. Oh, actually, you know, I swapped the arguments that way, right? There you go. And then there is the if statement. And what if does is, so first you got to have 0 or 1 as the outcome of a comparison basically on the stack, right? And let's forget test and write something. Simple test case again. Say we have already 2 arguments on the stack, A and B, and we want to know if one is smaller than the other, right? And if, so now the result of the comparison is 0 or 1, and if now basically pops that value at the top of the stack, and depending on whether it's 0 or 1, it executes either the if or the else clause, right? And so if that's the case, then we just want to print smaller, right? Else, it's obviously greater or equal, right? And then you terminate the definition of if with then. And that's of course a little bit confusing to, you know, people that are used to algol style programming languages, but that's the way it is. Okay, so 3, 4, test, smaller, okay? 3, 3, test, greater or equal. 4, 3, test, greater or equal. Alright, so now you also know how to do comparisons and ifs and else. And, you know, the usual operators are there. What you would expect, right? I think we even have something like smaller or equal than. No, we do not. Alright, but you get the idea. Everything that's needed is available. And in the next video then we are going to take a look at compiler extensions and how we can implement a recursive version of the factorial function, how to deal with forward references, and then of course there's even indirect recursion, right? So something like the classic odd-even example, right? A number is even if 1 minus the number is odd, right? A number is odd if 1 minus the number is even, right? So this is a mutual indirect recursive version, recursive definition, even calling odd, odd calling even, and requiring forward references again. So yeah, let's have a look at this in the next video. Until then, guys, thanks for watching and thanks for your interest in that ancient alien language force, which is kind of fascinating, and I hope I can share some of my fascination with you and that you might, find it interesting enough to also pick up some force system for your 8-bit micro maybe, or maybe even your microprofessor. Give it a try and, try something different. It's kind of interesting. Alright guys, until then, thanks for watching. Bye.